So in this talk, I'll consider our class of linear systems. And it's a particular class of linear systems where we have a external springs, but the input u is required to be sparse at each instant of time. These type of systems arise naturally in many applications in controls and dynamical systems, particularly in motor control, where you might be moving, but only a very small fraction of all the neurons can be activated for a particular disturbance at any given time. Or in practice, it may also arise due to constraints that you want to impose when you're inside the control. So you might have energy constraints, for instance, and so you don't want the input to be on all the time. So there is a lot of great work that has been done in this area over the past few years. In particular, questions of design controllers with sparsity constraint, how do you schedule actuators in a control system. The work that I'll be presenting focuses more on the question of observability and invertibility, which has to do with the question of, given the output metrics, yk, is it possible to estimate of the initial state, x0, and that will be a classical question of observability. But in addition, in this case, we also want to estimate the unknown input uk under the assumption that it is sparse. And of course, what this means is that the dimension of u could be very, very large, as opposed to in typical control systems where the dimension of u is relatively small, even relative to the dimension of the state. So over the past few years, there's been growing interest in this area of observability for linear systems with sparse inputs. We call this one of the first papers in ECC 2015, where we had the first sufficient conditions for observability. What I'll be presenting today will be in two parts. The first part, and that would be the longest, would really be deriving conditions that are both necessary and sufficient for observability. And the idea is to do this via classical techniques like L1 reading such. In the second part, I'll be from the finite or horizon case, where the number of inputs is finite, to the infinite horizon case. And in this case, the question is whether I can invert the system. So let me get started with the first part. And this is really work that's done by my student Kyle Poe in collaboration with Enrique Machada at the Johns Hopkins University. All right, so as I said, we consider a linear system in discrete time. And the major difference is that the dimension of u is potentially very large. And we assume that it's sparse and the level of sparsity is less. And again, notice that we assume that each input is sparse and with the same upper bound on the level of sparsity. So as it's well known, we can write the output sequence in this case as a sum of two terms. The first term depends only on the initial condition, and the second term depends only on the input sequence. The first term is really the classical observability matrix times the initial condition. And the second term is the matrix of Markov parameters of the system times the input sequence. And this is really for notation. From now on, you're not going to see these gigantic set of equations, but this is really the simple equation I want you to keep in mind, and this is going to be the key notation throughout the talk. That the output sequence is equal to the observability matrix times the initial state plus the matrix of Markov parameters times the entire input sequence. And again, the idea is that this UN now, it's very, very large in dimension, whatever the dimension of an equality, times n, which is the number of steps that we use. So again, I repeat the question. The question is, what are necessary and sufficient conditions on both the observability matrix and the matrix of Markov parameters, under which we can recover x0 together with the sparse inputs? So if the problem was very simple and basic linear algebra, we would immediately just jump at it and say, well, we just need to impose some rank constraint. We would like the observability matrix paired with the matrix of Markov parameters to be full ranked, so the kernel will be 0. Is that possible? Well, if there is no inputs, that's 3CS, and that's classical observability from 1950s. that what we need to reinforce as a necessary condition is that that observability matrix needs to be full round. The challenge comes from the input, really. So at the other end, suppose for the moment that there was no initial state, that it was 0. So all we have is that the input-output relationship is via the matrix gamma. And so can we impose that gamma needs to be full rank? And so the answer, and here's the key challenge, the answer is no, because we have a large gamma matrix, even more than that. Okay. So in general, this gamma matrix will have a large kernel, and what we need to do is to exploit the sparsity of U in order to solve it all. So just what do we mean by sparsity more precisely? So a little bit of notation on the sparsity patterns. So if you just give me some vector U, and that vector is constrained to be S sparse as written here, so delta is going to be just the support. So the locations of the non-zero entries. Okay. Now, what is it that we need though is not quite this. What we are going to do is that we're going to have a sequence of inputs. So this is capital N inputs. And we want each and every input to be sparse with the same sparsity level. So that induces a different support on the sequence of inputs, U sub n. And we're going to denote that with delta ns. So denote to refine that I have capital N inputs, and each one of them is supposed to be S sparse. So again, this is the support. So these are the entries, the locations of U, where I am allowing the entries to be non-zero. And that pattern of non-zero entries is unknown. We don't know it at priori. Now, notice though that these and that are not equivalent. So what you have at the top is classical sparsity. There has no structure. All of the are just a vector, and the non-zeros can be any chord. This is highly structured because I have a vector. It is supposed to have n blocks, and each block is supposed to be sparse. However, for the pedagogical reasons, it's going to be simpler to say, okay, what if the input sequence was sparse? And if this input sequence has n blocks, right, and each one of them is supposed to be S sparse, the total sparsity is n times S, right? So this is why you're going to introduce this notion of average sparsity, because the total number of non-zero divided by n is on average S. The point is that this is really, this is kind of classical sparsity. We just require the full sequence to be any S sparse, but that's not what we want, right? So what we really want is in the middle, but I'm going to use this thing at the bottom just to say, hey, if this was the case, could I use classical sparsity results? And the answer is that be yes. And that's exactly what I'm going to use next. Right? So back to 2003, when sparsity was very popular, the way in which you would solve these problems would be as follows. So suppose that I tell you that the output y is equal to the gamma matrix times U sub n star as input sequence, and that true input sequence is sparse on average, or SN sparse, which applies everywhere. So in order to find that UN, what we do is that we set up an optimization problem where we would like ideally to find the solution to this linear system, but we would like to find the sparsest possible solution. And that's NP hardware general, and so we typically use a convex surrogate, which in this case is the L1 norm. And so that gives to the classical setup for sparsity, where you minimize the L1 node of the entire input sequence, subject to the fact that it produces the given out. Okay, so it is setting gamma is given, y is given, and you're just trying to find it. So a classical result from 2003 is that what are the conditions under which the solution UN is unique, and is exactly equal to the UN star that you start with. And this property is a property on the gamma matrix, and is the so-called null space property. So there is this famous theorem that says that this L1 minimization problem, the solution to it, would correspond exactly to the S sparse on average solution you started with, if and only if this null space property is satisfied. And what is this null space property? So the matrix gamma is not full rank, so you didn't have a vector in the kernel. What you do here is that you measure the L1 norm of that vector eta, but restrict it to the sparsity pattern S. And the idea effectively is that the L1 norm of that vector, the kernel, needs to be sufficiently small, effectively less than half the norm of the total. Okay. So this is, again, I repeat, the null space property, and it simply is a property that constrains the null space of the gamma matrix to satisfy this constraint. And notice that this is done for every vector in the kernel. And this is done also for all these sparsity patterns. Right. Okay, so that's this view we are done. Well, no, because this would be if the input sequence was ns sparse. But we know that that's not the case because we want each and every block to be sparse. So beautifully, we had a paper in 2021 that was really trying to understand what kinds of sparsity patterns can be recovered via ML1 minimization. Can I change the pattern? Can I do block sparsity, or which variety of structured patterns? And indeed, if you compare the two slides, it's essentially identical. You can use the same and one minimization. So no change, just solve the same problem, even though the sparsity pattern is different. The condition is, again, that L1 minimization is going to find this pattern where each input is sparse, if and only if this null space property is satisfied. And the null space property looks identical. All what I've done is change the sparsity pattern. Okay? And so the answer is therefore that yes, there are exact, necessary, and sufficient conditions for the recovery of income, which is where I was aiming for here. And the results in this 2021 paper are about who general. In fact, this is true for a variety of sparse in patterns that have the property of being asimplicial complex. But one particular case is the one that appeared. All right, again, this is if there was no initial state. So now back to the problem that I started with. What if we now have Y being the output of a linear dynamical system with sparse inputs? And so this means that there is a true initial state and there is a true sequence of sparse inputs that generated the output. So we are going to solve the same problem as before and one minimization, but with just one modification, which is that there's an extra term here, right? The term that depends on the initial condition. But notice that it's a little bit asymmetric because we're, the input is sparse, but over x0 we have normal strengths, x0 from Bn. So we're gonna solve this problem, but we cannot apply classical sparsity technique, everything I just said, because the x0 is extra there, and that's not part of the utilization problem. So as it turns out, the same type of condition applies. So the main theorem of our work in CDC 2023 is that L1 minimization, so the solution to this convex problem, gives you exactly the true initial condition and the true sparse input, if and only if the following two constraints are satisfied. One, the system must be a circle, as you could expect, right? It's going to be a necessary condition. But the other one is that now we have this null space property over the sparsity happens. But if you compare these to the previous slide, the main difference is that in the previous slide I only had gamma, right? Now there is gamma times the orthogonal projection onto the orthogonal complement of the observability subspace. Okay, and you should expect these kind of results because effectively all I've done is, if you want to prove this in one line, it's not the exact proof is just take your system of linear equations, multiply on the left by your orthogonal complement of ON, so that you kill this term, right? And then apply the results from before. So that's the basic idea. So long story short, this null space property shows up all over the place, and now it is to be applied to the projection of the matrix of Markov parameters onto the orthogonal complement of the observability. All right, so are we done that? We can now check immediately whether a system is observable or not, and whether we can recover the sparse inputs on the initial state. Well, this would be the condition. It's reasonable there. The issue is that checking this is obligatory. Going back to the definition a couple of slides ago, right? I need to compute this ratio over all possible vectors in the kernel and over all possible sparsity patterns, find the maximum, and then check whether it's less than 1/2. That would be the operator. And that's combinatorial, particularly because there is an obligatory number of sparsity characters to be checked. So the key question we ask here is whether there are maybe upper and lower bounds to this quantity that are easier to compute. Easier in what sense? Well, another challenge is that this is not only combinatorial, but also has any rows, the matrices become bigger and bigger and bigger, so it also is exponential on the number of steps or the length of the sequence, which is a problem. So what we're trying to do is we at least made it simpler by eliminating the dependence on M. And one way to make it simpler is, this is the x-axis here is what we need to check. We need to check whether it's less than 1/2. So here would be a good region to be if the system is observable. So if I could find a lower bound in red and an upper bound in blue, if I know that the upper bound is to the left from 1/2, then I know that that's a sufficient condition for observability. If on the other end, I know that the red, which would be the lower bound, is to the right of 1/2, then I know that this condition is violated. So if I could find those upper and lower bounds, then I would gain business. Obviously, if the upper bound is 0.5 and the lower bound is less than 1/2, I go. So that's exactly what we need. And so this is the second theorem, which says that the quantity that I want, the null space property, which depends on n, can be lower bounded by just the null space property of only one step. One step because this is just the standard matrix of Markov parameters, and this is the standard sparsity pattern. Okay. And at the other end, it can be upper bounded by the null space constant of the projected matrix gamma 1, only with one step. And the same, the classical sparsity pattern. And the beauty of this is that even though the lower and the upper bound are state combinatorial, first of all, they don't depend on n. That was the big advantage. And second, because sparsity is studied for so long, at this point there are random mount type algorithms for evaluating null space constants for classical source. And so that's exactly what we did here in the experiments, which was we generated a large number of linear systems at random. For each linear system, we keep a random initial condition and generated a trajectory. And we did this multiple times for many dimensions and many sparsity levels. And therefore, we had now, imagine 1,000 or whatever number of L1 minimization problems to solve. We solve them all. And then we check, do I get the right initial state and the right initial input, yes or no, or do I fail? And so we are measuring the probability of error, which is opposed 1. So blue means that you failed, and white means that you succeeded. Is both. Okay. And so as you can see, and as expected, to succeed, the y-axis here is the sparsity level. So the sparser the solution, the easier it is to recover. And P here is the output dimension. So the larger the dimension of the output, the easier it is to recover. So that's why in this quarter here, that's what we succeed. And complementary at the other end is one you free. So now, if you check only the lower bound, which is in red, that gives you the everything that is surrounded by a red region over there. And as you can see, in most cases inside the red region, you have dark, which means that you failed, and as expected, right? So if the lower bound is about 1/2, then you fail. At the other end, the blue region is if the upper bound is less than 1/2, then you succeed. And everything inside the blue region is fully white. And again, the other interesting thing is that in these experiments, you see that there is a phase transition in between, and that the upper and lower bound are not that far from each other. This is. Okay, so to summarize the first part, and the second part is a much shorter, or the one. In this first part, we established necessary and sufficient revisions for sparse recovery and observability of the initial state. And the beauty of it is that this is just classical L1 visualization, even though this is applied to dynamical systems, and the type of sparsity for dynamical systems is different. Second, we got conditions that are either necessary or sufficient, but are independent of the length of the sequence. It's easier to compute. But again, everything we did is for finite n. And so the question of infinite or Kreis or invertibility we made open. And that's precisely the subject of the second part, where we want to mirror the infinite Kreis. So in the infinite Kreis, you worry about the question of invertibility, which means that you begin with the set of inputs, and then for a particular initial state x, you map that to the set of outputs. And so what you worry about is the system would be left invertible if, for any use of condition, there is a unique input sequence producing any possible outputs. Okay. So this is classical, and in the classical setting, Rn is the set of inputs where you can have any. So the main modification here is we would like to restrict the set of inputs to this set of sparse inputs. So the modification of invertibility, or the definition, is simply that is going to be left invariable with respect to a set u here. So that's why you call it left u invariable. And the definition is the same. It's just that the set of inputs needs to be restricted to whatever set. Okay, so that's sort of the basic definition. So if we go to linear systems 101 and we ask, well, what was the classical and well-known result for convertibility of linear systems? Then this condition on the Russell MAQ shows up, that it is our normal rank, which is what's really here. So this is a condition on the parameters of the system ABC. So it would be super nice, and our wild guess was, aha, we just need to do the same for the sparsity. Each input is going to be sparse, right? If you think about this, B is B times U, but the U is sparse, so now I could restrict it to the sparsing pattern. So I would have B restricted to S and B restricted to S. So if this was true for all sparsing patterns, then I should be in business. That was our guess. The answer is that life is not always as easy. And so this is true, but only if the S was fixed. What I mean by that is the first input has some sparsity pattern, but the second input is going to have a different one, and the third one is going to have a different one. So if the sparsity pattern was the same for all time steps, then this issue would be okay. But as you can imagine, that's really overly restricted. So this generalization of this type of condition that in the spectral condition is not true. So then we move into, okay, what other conditions are there for invertibility? And this is the second one that is well known, and this is a geometric condition. So with this geometric condition, to begin by defining this set V, which is the set of weakly unobservable states. Weakly unobservable states means that X is weakly unobservable if there is an input such that the alpha is 0. Okay, all right, so that's what we did, I'm sorry. And if we go back to invertibility 101, linear systems, the system is left invertible if and only if these intersectional subspace type conditions hold. In particular, the simplest and almost obvious is the second one, that says that the kernel of D and the kernel of D needs to be 0. This is kind of obvious, but it needs to be necessary, because if B or D had a kernel, then you would have more than one U, but this is the same output, right? So then you would be in trouble. But notice that this weakly unobservable subspace shows up here, so by intersecting that, you will get some of the quizzes. So this is what we knew from linear CT1. So all we did was, let's generalize this to the case of sparse tuples. And so the weakly unobservable set, either for sparsing, the definition is just that, and there are really anything, is that there exists sparse inputs. That's all what we wanted. And once you do that, voila, then you get the conditions that you want. So in order to guarantee invertibility for sparse inputs, all what you need to do is to take a B matrix, restrict it to the sparsity pattern, take the D matrix, restrict it to the sparsity pattern, and then identically the same conditions back. So all you need to do therefore is verify a condition like the classical one, but for all possible sparsity carriers, by the way. Okay. In last slide, the same can be done for the third kind of invertibility condition. So another one that is a rank base was simply to take the matrix of Martu-Brunner's N, and the difference of the rank between the rank of gamma n and the rank of gamma n minus 1 needed to be equal to m, which is the dimension by x. That's the classical result. So the extension of that to sparse inputs is, I'm just spelling out here what gamma n really means. As you can see, it's the matrix of Markov parameters, but I'm emphasizing just that there are different sparsity patterns in different colors. And the analogous of gamma n minus 1 is what you imagine, but just to give at the second sparsity can. So that's the main modification relative to this. And then the difference of the two is not equal to the number of inputs, but rather the cardinality of the first set, which is the number of active inputs of the first step. So again, very natural generalizations of these classical results. So to summarize, I think we have now necessary and sufficient conditions for recovery of the initial state and sparse inputs. We have done that both in the finite horizon case as well as in the infinite horizon case, where we have notions of invertibility that are both geometric, rank-based, or spectral-based, and putting the two of them together to be able to get the results that apply to both the finite and infinite horizon cases, the next steps. Thank you.
Then you could want to talk or take questions.
Yes.
I was wondering, how does it differ for like an unknown input observer? So if we would just use the conditions for the unknown input observer and use sparse inputs, would it not recover the sparse inputs?
So first of all, if the inputs are null, but not necessarily sparse, then you need that gamma matrix to be full rank, which is violate in this case because we are in a situation where the number of inputs is very large. So all the classical, the sparsity is you need to you cannot do this without exploiting the very specific properties of the sparsity patterns, and that's the big challenge.
Your research is on analysis of a system. You using your method can we design sparse control or sparse controllers?
So we've not looked into that. I think Professor Josek has some talks exactly on the question of how to design controllers. So I think I'd advertise our talk later today
After the coffee break.
Oh. Yes, it might be the same question again, but can your analysis show that in the sparse solution that this particular input is never active? We can throw it away and not use the actuator at all.
Okay, yes. So indeed, I think in the very first paper that we had in ECC 15, we looked into very specific algorithms, particularly in the online setting, where we would exploit such constraints. Like, to be very specific, right? I said, we have this L1 minimization problem. Your complaint could be, but this is kind of really big, even though it's convex, time you solve such a gigantic problem. And so in that ACC paper, and I didn't talk about that today, we said, could I do this online in the sense that I first compute the first sparse solution, and then given that I compute the next, and so on and so forth. And then we realized that for the specific algorithm that does it in this recursive pattern, you would get non-unique solutions every now and then, because that algorithm is different from solving the other. And then we began exploiting things such as the one, well, if I know the sparsity pattern, right, I can actually constrain it at the algorithmic level and exploit that. So long story short, the answer is yes. And we've done that But when it comes to the theoretical guarantees, I don't think that for the specific algorithm that does that, a fear or supply.
Questions? I have one last question. So in the work, do you assume that there's only one sparsity shift? What happens if there are multiple sparsity shifts? Does
So I think that the answer is the same as for just classical sparse, where you say there is a sparse vector such that when I'm applying matrix is once you derive conditions for reordering that vector, you are making the assumption that the solution is unique, and so these necessary association conditions require that. That being said, and I worked for many years, at least 10 years, on another related area which Murray calls subspace mastery, where you could have this gamma, the equivalent to the gamma matrices that are called dictionaries. They could have multiple blocks, and each block could be low rank, for instance, and then you have non-unique solutions. But then you wanted to find a solution that comes from the right block. So long story short, there are many extensions, different patterns that would potentially echo what you're saying. But if you want necessary and sufficient, I think uniqueness, I conjecture, I'm not sure, I conjecture is needed. Because for once uniqueness is out of window, I think all of the conditions I know are only just sufficient.
I'm a little jet lagged, so please raise your hand if anything is unclear in the talk. Okay, so I'm going to talk about global performance guarantees for model predictive control under sparse local communication. So first, we're doing some terminology, so we're all on the same page. So my work focuses on the control of plants that are a network of dynamically interconnected subsystems or nodes. Right? Here we have a network of 9 nodes. Each node can have the dynamics that you want. It can be pendulum, it can be slow, whatever. And the ones that have an edge between them are couples. So in this graph, everyone's dynamics will eventually affect everyone else's dynamics. But if you think about discrete time case, then in one time step, only the ones that are connected by edges will affect another. I work with the discrete time linear saying, you're probably familiar with this. And the network structure is embedded in the sparsity pattern of the A and B matrices, right? So, for example, if you had a grid like that, and every node had one state, then your A matrix will look something like this, right? So if we look at, for example, the first row is which systems affect subsystem number 1, right? And only the first and second ones are allowed to be non-zero because only 1 and 2 have a connection. Similarly for all the other ones. So this is the notion of sparsity that I'm dealing with. It reflects some kind of network topology. Okay. Now we talk about centralized and distributed controls. The centralized controller is I have my network. I don't really care what the structure is. I just take one controller, I communicate to it from everybody, and then I do control like that. So a simple example of that would be we have our standard state controller, a state feedback controller, right? You take the S from 1 through 9, nodes 1 through 9, you multiply by k, and then you send out let's say we have 9 controller, then we just send out U1, U2, U3 to D. This is very boring, and this is not also not that practical, depending on the size of your grid, right? I have a power grid, it spans the entire continental United States. I'm gonna have one controller, and you can see how this will be a problem. So what we're more interested in is distributed control. So now, every node gets its own little controller, that I'm going to call a subcontroller, but they have to communicate with each other. And in the most extreme case, you can have everybody communicate to everybody. It's not that much better, but it's a start, okay? And so in this case, we have global, also all communication. And what kind of control can you do with this? You can do the same thing as centralized control. So for example, if you have a state feedback control, what you're going to do here is every single node is going to get x1, x2, x3, x4, all 9 states. But each subcontroller only needs to compute its own output. Okay, so now that corresponds to everyone gets all the states, and then they multiply by one row of k to get the input that control input that it wants for its own subsystem. Okay, And then now going like that, we get to the final and best version of this, which is a distributed controller with local communication, where each self-controller now, instead of communicating to everybody, only communicates with some neighbors that you specify. So for example, in this picture, I'm just having them communicate with the ones that they're coupled to, but you can also have a little bit more communication depending on what you want. Okay, so and for this to happen, you can still do state feedback control, but to do that with local communication, you would want your K matrix to be sparse with some pattern. For example, in this picture, K actually has the same sparsity pattern as A, it causing the sparsity patterns to match. Okay, so for the rest of the talk, I'm gonna focus on local communication, and this is just a special type of sparse. Sparse would be, instead of having all of this bunch of communication, I just have less. Okay, but local means I have less communication specifically in a way that this communication topology is sort of related to kind of the spatial configuration of the nodes. So if I have a grid of 100 nodes, if I only let the corners talk to each other, that's still sparse, but that's not local, right? You want like each one to talk to the nearby ones. Okay, so now we can talk about control. So in large networks, as I mentioned, distributed and local control is preferable over centralized control. Centralized control is often not possible if your system is like a huge router. In the distributed case, right, you can have less communication load, and you can also have more scalability. And the reason I say that is, let's imagine we have a node of a system of 100 nodes. Yeah, if I communicate with everybody, I get 100 sensor readings, and I do some computation on that to get my output. But if I only communicate with like my 4 nearest neighbors, then I only compute on 4 sensor readings, right? And so if you're doing like a matrix multiplication or an optimization, your computation is smaller. And so that's what we mean by scalability. Each node only has to compute like a problem whose size is not dependent on the overall system. It's only dependent on how many neighbors you talk to. Now, of course, on the flip side, in theory, this will result in performance degradation, right? I'm optimizing over just a little bit of information over a lot of information. And here's one paper that talks about this. But the thing I'm going to talk about today is that actually for online control, this doesn't have to be the case. So even you don't talk to 100 nodes, you just talk to a bunch of close by nodes, you can actually perform just as well. And this is published from a couple of years ago, which was also surprising to me. Okay, so now we're gonna do the map to show this. So the standard model producer control, I assume everyone knows what it is, but I'll just say it just in case someone doesn't know. So offline control is like I have one controller, I take the X, I do some computation, I get the U. Model predictive control is like every time step, I read my current X. So that's what displaying here, x not equals x at tau. So that's my current time step. And I say, I'm gonna now predict the future. What's the best course of future actions that I can take subject to my objective, which are the F's, and some constraints. So I have to follow my dynamics. I have to stay within some bounds, and I have to satisfy minimize some objective. And then I'm going to predict over a future horizon capital T. And after I do all of that, I'm only going to take the first U that I get, I'm gonna actually apply it to the system, and then I do it all over again. So every time step, every time I get a reading, x of tau in this case, I do this optimization over horizon, and then I take one step towards it, and I do this over and over and over. Okay. Now in this formulation, it's not very clear what like local or sparse communication really would be in the way that I've defined it. So we're gonna go through a slightly different formulation. Basically, we're gonna now, instead of minimizing over x and u in the future, we're gonna minimize over these larger variables phi x and phi u, and these are simply just maps from your current state to your future trajectory. Let's see, so this one is the same. You can kind of make that equivalence. This is essentially the dynamics constraint, because this is just A's and B's, and then these are mistakes. So there's a nice theorem in paper that says this constraint right here parameterizes all the closed loop maps that are coupled by stabilized controller. And in plain English, this just means I can go between these parameterizations. I will not lose any solutions. So we're going to go into this different parameterization. And the reason that we go to this different parameterization is that this actually allows us to include local communication constraints as sparsity constraints on our decision variables now. Because if you have that side, if you have some sparsity constraint on X and U, that doesn't necessarily tell, it just tells me I didn't use this actuator. It doesn't tell me how much communication I used to compute that actuation. But this one, if I get these things to be appropriately sparse, then that will directly correspond to the picture I was showing earlier, which is I could compute my local actuation with only a little bit of communication between yours. Okay, and that's sparsity constraints. Okay, so it's kind of like a refresh of the other. So we have a few papers from much earlier that say, you know, like if you do MPC like this and you force your variables to be sparse, you communicate less, and you can be pretty scalable, and we have some simulations with that. But that's actually not what I'm interested in today, but I'm happy to talk about it offline. The thing that I wanted to add is, if I add this constraint, it's the same as in some cases if I don't add the constraint at all. So even though I force everything to be sparse, the overall performance is going to be the same. Okay, so now we do the actual math to show this. So the way we approached this was we asked, okay, we have this constraint optimization. How do these two constraints, which correspond to the dynamics and the local communication constraints, how do these affect the space of reachable trajectories of states and inputs? So remember, for MPC, we're always trying to look into the future and find the best trajectory. The question I'm asking here is like, which futures are available to me, right? What's the space of things I can minimize over that satisfy these constraints? So I'm gonna go a little bit of math. So we're just gonna redefine some variables. We have two decision variables. I stack them together. Due to this property, actually, the first part is always identity. So the free variable just becomes phi2. Okay, and then the trajectory you can actually write. So the trajectory now, I'm stacking the future states with the future inputs together. And you can write that as phi2 times your initial condition. So we're just interested in like, what is that space of available trajectories look like? Okay, so first thing, let's say, forget about all these state downs, local, whatever. We just care about satisfying the dynamics, which we always have to do. If we just care about satisfying the dynamics, then these are all the possible trajectories that are available to you for you to optimize over. You have, right, this is the same thing as above, and you just have to have your decision variable satisfy this equality constraint, and then that's the space of trajectories that are available to you. Okay, now we have to add our local communication constraint that I was talking about. For the local communication constraint, if I add that, then the space of available trajectories to me becomes this second line over here, right? It's basically the same, but you have one more constraint. Okay, so hopefully it's sort of obvious, right? That this has to be contained within that. Right? It's the same, like almost the same thing plus one more constraint, right? So it can only be smaller, it cannot be bigger. Now we're interested in the case where they're equal, because if they're equal, then your performance is not affected by adding these other constraints, right? You can still search over the same space for your minimization. And that will be true for any objective, for any state and input constraints, right? Because the space is the same. So if I search with it, and I'm gonna get the same option. So now we have to write the math equations for these guys. Okay, so first one, this is all the trajectories available to me if I don't care about local constraints. Okay. So we have a multiplication and we have the alpha constraint. So let's just parameterize the constraint. I'm gonna write this constraint up here as some particular solution plus some homogeneous solution times some free variable. Okay, the free variable is lambda. So now I parameterize my phi, but I still have to write out my trajectory. So the trajectory, so I'm gonna cut off the first few rows of my phi variable to get phi2, because the first few rows are actually fixed. That represents like your trajectory has to start at your current initial state, so that's not like a variable. Okay, now I can write my trajectory, so y is equal to that thing times the initial state. So you just kind of plug that in. It becomes, again, a particular solution plus a homogeneous solution. Time is a variable times your initial state. We're almost like this is kind of ugly because we don't like our free variable to be between two fixed things, right? We like our free variable to be on the side. So we're just gonna do an algebraic to bring it out to the side. So instead of using x naught, which is our current condition, we're gonna make this huge matrix, which is basically a bunch of scaled identity vectors, matrices. And that's gonna let us to write lambda x naught instead as x lambda. So now we have the free variable on the side of the equation. Now we can say something about how big this space is. So you can write your space like this, where I've just replaced the capital lambda with smaller lambda. And the size is just the thing that free multiplies my free variable, right? The rank of the thing. So the dimension of all the future trajectories I can reach is the rank of this matrix over here. Okay, we're gonna save that, because now we have to do the same thing, but for the local case. Okay, so the local case is with almost the same thing, plus that one additional constraint. And we're gonna parameterize the communication constraint. Again, well, you just write it out as like a subspace constraint, or you parameterize your equality, whatever you want to think. The details are in the paper, but the math is really ugly, so I'm just going to give you the ending. And the ending is that the dimension of the futures available to me if I'm constrained to local communication is also a rank. It's the rank of this thing. Now, the previous slide, if you remember, it was rank of ZHX. This new one is the rank of ZHX times this additional thing. So now we want to think about like what the effect of this thing is. So roughly speaking, F represents your communication constraints, which are encoded in your sparsity constraint. The more you allow your subsystem to communicate, the lower rank F will be. The lower rank F will be, the higher rank this guy will be, and the higher rank everything will be, right? So, okay, intuitively this should make sense. If I let there be more communication constraints, my space of available future trajectories is big. Okay. So, yeah, as a reminder, we're trying to find the case where the two are equal, because that would mean performance is the same. So they're equal if the two sizes are equal, right? Because one is contained in the other. So if their sizes are equal, they are in seed space. So if this condition holds, then we have what we want. Now, we do a more rigorous analysis in the figure, but here's the intuition. Post multiplying by this 1 minus I minus F pseudo inverse F term roughly corresponds to getting rid of some columns of ZHX. Okay, so usually you're comparing the rank of this matrix with some columns zeroed out. So obviously one of them is gonna be likely to be smaller, right? The one with the local constraints. However, so if you have a less allowed communication, that means you zero out more columns and you're more likely to have reduced your rank and therefore your space of available trajectories. But it turns out ZHX actually has a very, very repetitive structure because of the algebraic property. Remember, X is the bunch of identity matrices. How many columns can you zero out from this guy and keep the rank? Well, really a lot, right? Because it's horizontally a bunch of identity matrices. I can get rid of like every single matrix. I just have to keep one identity matrix somewhere and I will still have the same rank, right? So by the same logic, it turns out you can zero out a lot of columns of this ZHX guy without changing the rank at all. So what that's saying is I can get rid of a lot of communication without changing the rank. And then that would mean that everything works out and performance is unaffected. Can remove any communication links without affecting performance. Okay, so practically speaking, what this means is if you're going to do model predictive control in the local way, then if you know what communication constraints you're going to put beforehand, you make these matrices and you just check this thing. And if they're equal, then you can proceed knowing that you have not made a performance difference with your constraints. So finish off with a nice example. So here we have 11 by 11. So this is 121 nodes randomly generated to be couples. And they're linearized, discretized swing equations, so you can think of them as pendulum if you like. And nodes share an height only if they're dynamically coupled to one another. So these are the equations if you're interested. Basically, it's a simplified toy model of a power grid for coupled pendulum. Okay. So on this guy, we ask the question, we have a rank condition, right? So we can check this. What is the strictest communication constraints, so the sparsest, if you will, that we can enforce without changing the performance compared to the centralized case? And then, of course, we check this by doing like a few hundred different random initializations, and then we check that rank condition, right? If they're equal, then we're good. And it turned out that the optimal case is that every node just has to communicate with nodes with which it shares an edge. So every node has its own little controller. For example, this red node has its own little controller, and it only needs to communicate to these guys, none of the other 118. And then this will give you identical performance as if you did standard centralized UBC. Okay. And then we have some simulations in the paper, but it's not very nice, or it's kind of boring because you show two trajectories looking exactly the same because they have the exact same performance. Okay. So the key takeaway that I have is that for linear local MPC, I don't know about nonlinear, these two cases can perform identically, right? And we have a result that generalizes across different costs and across different staking input and strengths. This is the paper. Then I briefly mentioned future directions. So one thing that I'm interested in is the relationship between network topology, actuator placement, and optimal communication constraints. Because the way I posed the problem today was saying, here is my system, here are my communications, and just tell me if it's a good communication. But in fact, a lot of the time we also get to design the system, right? So maybe you want to design your system in a way that lets you communicate less. Okay. The other thing that I didn't really have time, so I also work actually a lot on neuroscience, so I just wanted to mention into this group, because sparse networks, also known as the connectome, are in the brain, where each node is a brain region and each edge is a connection between your different brain region. And actually there's a lot of fun things to do here, I'll just mention two. One approach is to treat your brain network as a plant. So it becomes your network control problem. How can you control this plant? Using sparse control or using distributed control. So some of what I was on actually applies to this as well. And the other interpretation is think about the brain network as a controller of your body. And in that case, your brain is a sparse network controller. And you can also ask the question, how does this control the body? Like, what are the requirements, or what is optimal or suboptimal about it? And so that might be interesting. I'm happy to talk more. Otherwise, yeah, that is the other presentation.
Thank you for the super energetic talk. I take some questions.
Many thanks for the talk. So when you say that you run an edge when you have dynamical coupling,
When I have, right?
so you say that in your graph,
Yeah.
you were adding an edge when you had dynamical coupling.
Yeah.
So it means that the two variables that you connect are in the same, so are just multiplied or occur in the same diagonal
No.
concept.
So in this case, I actually first generated the squared topology, and now what I'm saying is, so every node here actually has two states, theta, the angle and frequency, and I first make my A matrix, I make all the AIIs, they're like the self term, and then I put an AIJ if on my grid they have an edge between them. It's just how I generated the random network. So that's that's too high, sorry. So these two guys down here, like let's say this is like node 1 and node 2, right? So then in my graph, like A between nodes 1 and 2 would have that shape. But if I was looking at like this one and that one, then A between 1 and 3 will be 0 because they don't directly coupled. Yeah.
Done.
So yeah, maybe you very basic questions. So here, my first question is, what do you mean by some sort of local information? Does this mean that just that the local controller is confident it only refers the neighbors?
Yeah, it's this example.
Why measure the state of the neighbor?
Yeah, you guys measure the states of neighbor, or in the output feedback case, the measures of the neighbors. Yeah.
And the another question: how you formally define this communication constants? It's just the communication constant are just somehow the part of information that is double to each local function.
So the way you can do it is if it was state feedback, for example, u equals kx, you can define the constraints by forcing your k to be 0 at some places. Because it's 0 there, you don't get to use the state information from that node, so then you don't communicate with that. That's one way we communicate.
Okay, and if it's a general nonlinear controller, it will be just the states to which it has access, right?
Yes,
Okay.
yes, exactly.
Yeah. Thanks for the presentation. As a follow-up question, if you have input coupling, can you apply the same reason into the optimality guarantees?
You should be able to, yes. So I think that would actually change. I think to be optimal at a minimum, yeah, you will need to communicate to the inputs to which your output holds. I think we might have had some simulation on that, but yeah, you should be able to incorporate it. The thing it will affect is how, like, the sparsity structure of the local communication, because then you will need to let your local ones also communicate with anything that it's input coupled to. With a ship.
With entire directory.
Sorry?
With entire directories around the prediction horizon.
Yeah. Yeah, it should.
And the graphs here are all undirected, and so it looks like the communications are symmetric both ways, and the effects of the coupling are symmetric. Do you have any intuitions or results for directed networks? Is it something
It's the same, actually. It's the same. It's just that, yeah, like then basically your constraint is also symmetric when it's undirected, and your constraint will be asymmetric if it's directed. Yeah.
So I had exactly the same question.
Okay. So is your intuition that in the symmetric case, you need to be connected to at least the neighbors that you're coupled to? In the asymmetric case, you need to be at least connected to the neighbors that affect you or that you affect?
That affects
Although-
you. It should be that affects you. You might need to. I'm 90% sure it's that affects you. Yeah.
As the characterizations that you had were really dimension-based, comparing branches. In practice, I think you can have very unique communication links, so the singular values of those matrices might have rats. Why in your results that doesn't happen?
That's an interesting idea. That's just not a direction that we thought of. We thought about the exact case first because we want to, but that could be something that we'll look to. The other consideration is, like, our results are actually really general, because you could also imagine, even if the same space isn't available to you, maybe if I optimize, I will say I find the same solution. So I think, yeah, in that case, maybe something like ST.
So I would present, so it's a French-Japanese collaboration. So here are some Japanese products from Shushu University mail, and some French products that are also from last CNRS, from the neighbor Unportil. So I'm gonna talk about polynomial optimization and how to leverage it to certify instability of some dynamical systems controlled by ReLU networks. So basically here we can imagine that you have a very complicated nonlinear system that we succeeded somehow to approximate the behavior of this nonlinear system by something that is almost linear, but that is controlled by value. So here you had your state X, your input W, and your output C. And the only nonlinearities arise from the fact that you control it with some pointwise value neural network. And so basically here, the value is equal to value on pointwise. And so here what we do is that we leverage the fact that the input-output relations of value can be captured by systems of inequalities and equalities. So here on the left, you have the graph of ReLU, right? So it's the max of 0 and Z. And so it basically means that W is either equal to Z or equal to 0, okay? So this off relation, you can encode it with degree 2 polynomial. So the one that is with them here. And you also know that W is the max. So W must be greater than 0 and also greater than Z. And so this, we just write it with two inequalities. That's very simple things, right? And so basically, if you want to use complicated words, you say that the graph of ReLU can be modeled by a semi-algebraic set. So a semi-algebraic set in this case is just a finite set of polynomial inequalities or equalities. So is this thing clear for everybody? Okay, so now we're going to basically, so every time we see ReLU, we're going to replace the ReLU input-output relation by this bunch of inequalities. And actually, so my co-authors showed in the previous work that this system here is unstable if basically this system of inequalities and equalities has a solution. Okay, so here basically I rewrote the input-output ReLU in ACOS. And here I want basically so here's this first slide. I want to say that it is equal to lambda x, and I want to find a non-negative lambda, because then I'm going to be able to write my state x of t as an exponential of lambda t. So if I want the system to be unstable, I need lambda to be non-negative. And the initial condition of the system will be basically given by the x that is a solution of this. So that can be a bit confusing to have x and w here and also here. But here, so the x that is there will be the initial condition of the state. Okay. And of course, there is a trivial solution to this system. If you don't restrict x w to be different than 0, well, x equal w equals 0 is the solution of this system. So this is not what we want. So we assume that xw has a norm different than 0, and without loss of generality, by homogeneity, you can just assume that xw has norm equal to 1. Okay. And so I'm a polynomial optimizer. I actually don't know much about controls and control of systems. So basically here what I see is a bunch of polynomial inequalities. So this is the feasible set of my polynomial optimization program. And I like to have a nice objective function. Then I can pick one, doesn't really matter for this problem. So let's say I have a polynomial f. Then I want to solve this polynomial optimization problem. And so here I put this here constraint, okay, because I want xw to be different than 0. And now I'm gonna bother you a bit about polynomial optimization and how you can tackle this complicated problem with convex relaxations. So is the setup clear for everyone? So now I'm gonna focus on how to solve this for this specific polynomial optimization. But first I'm going to recall how it works to solve polynomial optimization, and just a few words about related work. So this idea of encoding the value with these inequalities and equalities is not new at all. So it was used by different people, either from the optimization community or from the dynamical system community, for instance, to prove robustness of trade value networks. But also in dynamical systems, so for instance, to analyze the stability or the instability of such systems. So now let's focus on polynomial optimization. So who in this room never heard about polynomial optimization? Okay. So this is the setup. So here all the input data are polynomials. So the objective function f is a polynomial, and also the set of constraints is defined by polynomial inequalities. So we know the coefficients of f and we know the coefficients of g. So the blue things are the things that you know. And in practice, they are often sparse. So there are different higher sparsity that we can exploit. So for instance, correlative sparsity. So it happens when basically all the variables of your problems are not connected via products. So for instance, here x1 and x2 are connected because we multiply them. Same for x2, x3, but x1 and x3 are never multiplied to each other. So they are implicitly connected but not directly. And this is something that we can exploit. But for our problem, it doesn't work because everything is connected. And similarly, the notion of term sparsity has been used. So basically here, x1 and x2 are connected because they are multiplied. But you have a huge degree polynomial, but only 2 terms out of the possibly many. So here you have like 10,000 terms, but only 2 occurring. So this is also something that we can exploit. But it doesn't work in our case because we also have all possible terms. So here what we exploit is different kind of sparsity. It's the fact that, as we'll see after, our set of constraints is a discrete set. So we can actually use some nice theory of polynomial system solving to exploit this very specific structure. So to approximate polynomial optimization problems, we will use some techniques from convex optimization. That is a generalization of linear programming. So I guess everybody knows what this thing is. So in linear programming, you minimize linear function over a set of linear inequality constraints. So why am I reporting that? Because we're going to use semi-definite programming that is a somehow nonlinear generalization of LP, where basically we optimize over matrices with non-negative eigenvalues. So does everyone know what STB is? So who doesn't know? Okay. So great. So everyone knows that. So basically, our polynomial optimization problems will be relaxed with semi-definite convex relaxations. And so the idea to attack a polynomial optimization problem is that at the beginning you have a problem that is nonlinear, but finite dimensional law. And what you can do is embed this problem as the linear problem, but with an infinite dimensional decision variable. And so basically it's not too hard to show that minimizing f over x is the same as minimizing the integral of f with respect to a certain measure. So the space of measures is infinite dimensional. And what we're going to do in practice is that instead of considering this infinite dimensional probability measure, we're going to focus on specific discretization of it that is given by the moments. So what are the moments of the measure? They are just the integrals of the variable quarters. Okay, so for instance, the mass of a measure is the integral of ones. And then you have, the mean, the variances, and so on. And basically, when you do that, you can replace a measure by a sequence of moments. Why? And there is a matrix related to this moment sequence that is called the moment matrix, that is linear with respect to the entries, with respect to the moments of your measure. So here is one example. So this is just for self-contained. I'm not going to detail all of this, but if you want to look at the slide after. And so basically what's important here is that n is really linear as linear entries with respect to the moments. And if you have a measure, and if you compute its moments, then this matrix has always non-negative eigenvalues. That's a necessary condition. Okay. And now maybe you start to see the connection with SDP. It's because instead of optimizing over all measures, you're going to optimize over this gap. So you can try to find some y that basically represent a measure. So just so to recap on these polynomial optimization techniques, at the beginning you have your non-convex problem. You cast it as a linear convex problem over measures. And then you relax, so you truncate. Instead of considering all the measures, you consider a finite moment sequence. And that basically leads you to an SDK. And if you take an infinite number of moments, then you have some nice convergence walls. So basically you can start with 3 moments, and then take 10, then 20, and so on. And eventually, basically at the top of the staircase, you have FP, the minimum of that. And so very often people complain about this technique because they say, yeah, it's too expensive. I want to solve a non-convex problem very quickly. Sorry, but we can solve non-convex problems very quickly. And it's because basically, so this number here is binomial number, so it's quite scary number. But for some applications, you can basically reduce this size, and this is what I will show you just after. And I can skip. Okay. So let's come back to my ReLU problem. So actually, we have this input-output relation that I can write for every input component. So what does it mean that something is equal to ReLU? Well, it means that every input component Wi is either equal to 0 or equal to this Cx plus dW component. And let's just do something very brutal. Let's assume that all the inputs are zeros. Then what we have is a very nice eigenvalue problem. So we know how to solve that for a while, right? And we don't need nonlinear optimization stuff. We just need linear algebra, right? But here the important thing is that, so if you take something random, a generic matrix, generic n by n matrix, it will always has n distinct symbol eigenvalues. And the corresponding unit eigenvectors, you will have a pair of them. So x and minus x, right? And actually, you can do the same reasoning with more complicated matrix if some of the input components are non-zero. So basically, you have a disjunction of system for each case. So if the number of inputs is m, you have basically 2 to the m eigenvalue problems to solve. Okay? So basically, this system has always a finite number of complex solutions. So maybe it has 0 real solutions, in which case the system is not unstable. Or maybe it has, and then you can show that the system is unstable. So basically, so think about this eigenvalue property. So basically, lambda is the root of a univariate polynomial, right? So this univariate polynomial is the characteristic polynomial associated to the matrix, okay? But this actually holds even if you have non-zero inputs. So basically, you know that you have a discrete set of lambda. And so for instance, this can be the characteristic polynomial, or can be a more complicated polynomial. And actually, all the variables of the problem can be written as the function of lambda. Okay. So here, the reason why you have x1 squared and not x1 is because you have symmetries in the problem. So for every x that is a solution, minus x is also a solution. But so this is very nice, because so actually all these polynomials u0, u1, and so on, you can actually compute them with some nice problem basis engines that I will not bother too much with that. But so actually, if you want to solve the problem, you can use some symbolic computation tools to do it. And of course, you don't want to do that in practice because it's also very expensive. But what is nice here is that you know that any quantity that depends on x and w can be expressed solely as a function of lambda. And this we will exploit. Okay? So basically, the only interesting guides are the powers of lambda and the terms that are linear with respect to the states and the impulse pairs. And so, I mean, if you are to do the brutal thing, then you will have a huge matrix in your semi-definite relaxations. So that will be indexed by the whole world. And the size will be this. So imagine that m is 20, and this number is just a nightmare. But here we are considering the sparse variant of this that exploits the N4x factor. And the size is virtuals. So it's linear with respect to the input and output. And so what we proved a bit more, so basically this sparse moment hierarchy allows you to solve the problem asymptotically. And also we proved that if you take a nice stat, a nice objective function, and if the initial problem has a unique pair of solutions that will happen generically, then in your relaxations you will compute a rank 1 moment matrix. And this rank 1 matrix will give you the solutions. So that might happen for the power of lambda that is very large. But you know that it will happen. And yeah, so I stole this example from the previous paper by my co-authors. So that is not rocket science, but it basically shows you that if you start with this initial condition, then the system is stable and it converges here at the origin. But if you perturb a little bit and take this initial condition, then you have this instability behavior. So we basically computed this initial condition by solving the polynomial system. So I'm going to wrap up. So basically, I wanted to advertise the use of the sparse polynomial optimization techniques so that are very powerful to model complicated nonlinear systems. And so if you try to solve brutally your problem, of course, it's not going to work. But then you can always look at the problem in the eyes and use some more economical hierarchies. I wanted to emphasize that when you exploit sparsity, you can have some conservativity behavior. So it's cheaper to solve, but the quality of the bounds can be basically less good. But very often in practice, we reach the same accuracy bounds. And for instance, for this problem, it was the case. And then I also wanted to advertise that there is a book on the topic that we wrote in 2023, where you have other applications also in control, but also in quantum information and related fields like optimal Borg. And this is the link of the first paper, and thanks for listening.
Thank you. Questions?
Yeah. So, I think the problem was very clear for a single RLU function, but then if you're assuming you have a more complex neural network architecture with many layers of RLU,
Oh, you can do the same. So it's just that your system of linear and nonlinear equations will be more complicated, but generally, you will always have a finite number of solutions. And then you will be able also to index your matrices by using less terms.
But how the complexity of the problem would change, because the number of linear regions, if you have make it the hidden layers, it's growing somehow exponentially.
Yeah, so I mean so basically the behavior will be affected by different matrices that you use. So or to model your radio system, but I expect a similar indexing of the Wundt matrix. Yeah.
A couple of questions. The first one is very simple. Is what is choice of function f that we boosts, and does it work for any f, or are there specific choices?
Yes, it works for any f that is quadratic in x and w. So what we took for our experiments was x squared plus w squared times a power of lambda, or sum of powers of tau.
But x squared of w squared is 1.
Yes, so you can basically replace x squared plus w squared by y.
The second question is, if the system is stable at this point, has no solution, how will we detect?
So at some point, okay, I wanted to switch it, but now thanks to your question, I'm going to be able to find it. So basically, the dual of this moment problem that I mentioned is an SOS problem. And so basically, by using this dual Standard Core certificate, then you can basically satisfy step B.
And my other question pertains to the computational complexity. So for the LSR hierarchy,
Yes.
the typical conditions that I remember, where exactly referred that, let's say you have, if you build a graph on the variables and this graph is relatively squared, you may have pairs of products and numbers. So those were exactly the kinds of things that you said were not satisfied here.
Yes.
So what is the type of sparsity structure that allow you to get the results, since it is not too classic?
Yeah, so it's basically, so here we exploit the fact that the set is discrete. So we have a finite number of solutions, and that basically all the terms in XW can be written as a sum of linear terms with respect to X and W. So for instance, you have X1, X2, X3, so the product. Then you can write this as a function of X1 only. So that's what we call sparse here. But the powers of lambda, then you need all of them, and you might have to go to a very large power of lambda, that is basically the number of solutions of your system.
And how do you handle when lambda is real versus complex? Or this?
No, so if the system has a real solution, then you will be able to find this real lambda, this real non-negative lambda. And if your system has no real solution, then basically you won't be able to prove instability, but you will be able to prove stability by using these walls on the tools.
Oh,
So you finalize for value at non-linear, but maybe you can extend your method to general quantities.
Yeah. So for instance, if you take the saturation function, and I think you can write it as a combo of two value function, or maybe it's the other way. So and then it works also the same.
What was your motivation to analyze Levy system?
Oh, I mean, people, use all these activation functions that are popular. So they tried with renew, and then they tried with SAP, and then they tried with some smooth approximation of value. So the nice thing with renew is that it's very similar to Angle, right? It's systems of inequalities, and also it's so the advantage of value. So if you talk to a person doing machine learning, is that it's a function that is almost linear. So in terms of implementation, that's very convenient. But I have no options in LLU. Give me another system with other non-linearities. That would be also nice to try to apply.
My name is Neetu Joseph. I'm an assistant professor at ECC. And my talk is about sparse attribute control. This is in lines with the first talk. Let me discuss about estimate sparse control. So there is assume that sparse control has been applied. We look at the observations and how we estimate, or we invert the system and find out about the sparse control span. Master Lipper drop prepare under what conditions can we ensure controllability in sparse control? And if we know that the system is controllable under sparsity constraints, how do we design sparse control? So I don't think I need a very elaborate discussion in this game on the scenes sparse control the model. So control theory, conventionally, when you come to control theory, we think about mechanical systems, we think about power grids, we think about aerospace-based systems, etc. But control systems are very expanding beyond that, beyond the traditional boundaries. And we have biological systems, social networks, and physical systems. These are new types of control systems which have also been studied. So new systems might be new strategies because the constraints are new, and we need a new notion of optimality. So today we're going to discuss a new notion of optimality as sparse actuator control. So I'll tell you exactly what I mean. So sparse actuator control, in simple words, it means minimum intervention. So we don't try to control the entire system using all the actuators we have, but we try to control the system using few actuators at a time. So think about a big system that is geographically distributed, which has long opportunities to actuate, but it's hard to centrally control the system at all positions. So in such cases, we try to control the system using few possible options at a time. That is idea behind sparse actuator control. I'll give you a few examples. So think about biological systems that where you may want to apply some drop control. And you don't want to control each and every node of your body, but you want to control the minimal fashion. So that could be one motivation to do sparse control. Another thing is think about a network system. So system where your plant is at one point and your controller is at another point, and you have to communicate from between your controller and your plant. So there, what the constraint is a bandwidth. So you don't want to communicate very long sequence, but you want to communicate using a fixed bandwidth. And that sparse control can help because sparse inputs are known to be compressible. So if you compress it and you can set it and you can use minimum bandwidth to communicate your control. So sparse controls can help in resource computation, reduce the computational burden. Another example is social network. Social networks, so think about a big group of people you're trying to influence. Cannot go and influence each and every person in the group. So one of the options the marketing or advertising people might do is they will try to pick and choose few influencers, I would call, and they would, using the word of mouth, they would advertise their product. So if you pick few influencers, so influence few people in the group, and eventually those people can influence the people they know, and eventually you can influence a whole. So there, because of, I would say, budget constraints or advertising, so you might want to impose sparsity constraints on the tool. Another is an adversarial example called attacks, where you have limited access to the system. So think about larger systems which are geographically distributed, but they cannot actuate all the available actuators, but you want to work with few actuators at a time. So that motivates the idea of sparse actuator. So mathematically, you're looking at a big log sparse vector, or with only a few zeros. So few inputs are non-zeros, which are marked by the color boxes, and the white boxes represent the zeros. So the control input that has been applied to the system is always sparse. That's the idea. Okay. So what do we discuss in this talk? So in this talk, we look at sparse control in discrete time linear derivative systems. We enable this, it's easy. And we ask two questions. The first question is the divisibility question. So when does sparse control work? So if I restrict my control to be sparse, what is the price I take? Does it make my system uncontrollable? Or if it's controllable, what are the conditions under which it's controllable? The second question is, suppose I know that my system is controllable using sparse inputs, how do I design such control regimes? So please note that when I talk about sparsity, I'm talking about sparsity in actuator use. So control input that we applied every time is sparse. And we work with a linear state space model. So we have state of position x equal to a times c square minus 1 plus theta of uk, and we have linear observations which are noisy, and the constraints that we are going to impose a sparsity constraint, that is the L0 norm of the control input uk is much less than L, which is the size of the input. So we are trying to devise the sparsity. And we look at two variants of the problem. The first one is time invariant. In time invariant case, we choose a set of actuators and we are only allowed to use the same set of actuators throughout. In the time varying case, we can vary the actuators that we pick. So for first time instead, we pick certain number of actuators. The second time, we can change the actuators that we pick. But at every time, we pick only few number of actuators. So these are two different cases that we'll be looking at. Any questions so far? Okay, so first let's look at the controllability condition. So we start with the notion of controllability. So we know controllability means the ability of the system to drive the system from any initial state to any final state. And we test the classical controllability using Geiger-Kalman rank test or the PBH test, which is called simpler. So this is what we do, and we don't have any sparsity constraint. So suppose we have sparsity constraint on the control inputs. How does these conditions change? That's what we're trying to describe. So first let's look at the time invariant case. So the time invariant case is when we pick a set of actuators and we use the same set of actuators for the entire time. So here the controllability condition is start. So assume that in the subroute of that we choose for UK is S. S is part of the few entries possible. And then the system is controllable if and only if the span of this matrix. So we are picking S columns of B, the same set of columns of B at every time. So the controllability matrix changes as this. So instead of P, you should write E sub S. And everywhere we see UP, we should replace that with S. And system is controllable only if the span of this matrix union or all possible S. So we can potentially choose different S's for different inputs. But once you choose S, we should use the same S over the time. So the system is controllable if and only if the union of these different matrices but different values of the set S is equal to R per n. However, you can see that this particular set, this union, is a finite union of subspaces. So finite union of subspaces is another subspace if and only if one of the subspace contains R per n. So that's a standard resultant linear algebra. So what this result says that the system is controllable with time invariant support if and only if there exists a set S such that this matrix has full rank. Because it's a finite divided subspaces, there exists one set such that this particular matrix has R power n. In other words, what we are trying to say is that there exists a set S such that the system A times D sub S is controlled. So that this will be exactly the Kalman condition for this particular system. And therefore, we can write the p-Mesh test for this particular system, and the controllability condition for time invariant case reduces to the p-Mesh test, which is something where there exists an S such that the cardinality of S is sparsity over S, and it satisfies the p-Mesh test where AD plus B with B restricted to set S. So this is the p-Mesh test for time invariant case. But there's a problem here because we have to compute this for all possible S to verify whether this actual S exists or not. And therefore, this is an NP hard, this problem, verifying this is an NP hard problem. Not very interesting. So now let's look at the other case where we look at the time varying support case. So if we allow for time varying support, what happens is we can choose different support and different heights. So here again we have to write a span over all possible sets. But here instead of the common S, we can use S1, S2 all the way to Sk minus 1. So we can use different supports at different time, and then we have to take the span of the matrix and the new limit of all possible SPs. Again, this is finite divided subspace, and it tells us that there should exist a sequence of S1, S2 up to Sk such that this matrix has full rank. And that leads us to the Kalman rank net test. So what it says is that there exists a sequence S1, S2 up to Sk such that the controllability matrix descriptive to those sequence has full rank. One interesting observation from, again, computing this matrix also has computatorial complexity because we have to check over different combinations of S1, S2 up to Sk, and each of them has sparsity constraint on that. But what is more interesting about this result is that it tells us that there exists a state independent schedule S1, S2 all the way to Sk such that the system is controllable. In other words, if system is controllable using sparse inputs, there exists a sequence of sparse schedule, and that works for all states, irrespective of only the initial state of finite states. So you don't have to, if there's a sequence that works for there is just a sequence which works for any initial state and any final state, and doesn't change for the initial and final state. So once you pick the sequence, you can work with this for any initial and final state. But again, this is a combinatorial problem, and the question is, can we think about some similar conditions to verify sparse controllability? So one thing is, we can look at the necessary condition. We're looking at sparse controllability, which means system is controllable under sparsity constraint. So naturally, one necessary condition is that the system should be controllable without sparsity constraint. So one necessary condition for sparse controllability is that systems should be controllable in general without any sparsity constraint. So I would say that sparse controllability implies the general notion of controllability, which implies our normal Kalman test or EVH test should succeed. Another interesting observation is, we say that system is sparse controllable if Kalman prime test succeeds, which means that this controllability matrix should have full rank. But if you observe, the first few columns have the A matrix, few columns are pre-multiplied by this A matrix. So if you pull out this A matrix out, you can see that there is A matrix multiplied by something and this ds sub k. So the first few columns is basically a subset of span of matrix K. So what I can say is that if this matrix has full rank, it immediately implies that rank of A times B Sk should have full rank. Okay? Because whatever A can span, whatever S can span, A can also span. It is a subset of side of A. And now A and Psk should have full rank, which means whatever is the null space of K should be spanned by Dsk. And we have a sparsity constraint on S, which means there can be at most S columns in Dsk. And therefore, we can immediately conclude that rank of A plus S should be greater than or equal to N. This condition is violated that if you need at least S columns, which is greater than rank of, which is greater than N minus rank of A, which is a rank of null space of A, to satisfy this condition. To repeat, the subspace of the column space of A is covered by this part, and the null space of A should be covered by this part. Rank of null space of A is n minus rank of A, and then this part should compensate for the null space of A in order to satisfy this condition, and therefore S should be greater than or equal to n minus rank of A. So this is one necessary condition. The first necessary condition is that the system should be controllable. The second necessary condition is that the sparsity level should exceed n minus prime of A. So if these two conditions break, the system is not sparse controllable. Interestingly, we can also show that these two conditions are also sufficient. So in other words, if we have a system that is controllable, and if we pick a sparsity level S greater than or equal to n minus lambda of A, then we can ensure that the system is a sparse controller. So if these two conditions are satisfied, then there exists a schedule as well as 2 up to Sk such that the Kalman rank, that is the second end of this equation, is satisfied. Interestingly, this has no combinatorial verification. The first one is P dashless, and the second one is basically an autoplay. It's a mount or the sparsity. So it's much simpler, although we accept that when we talk about sparse controller grid, there should be a combinatorial condition. With this condition, it's much simpler. It's both necessary and sufficient. So to summarize, we say that sparse controllability is equal to two conditions: system is controllable and the sparsity level should be greater or equal to the nullity of matrix A. So if the nullity A is full rank, the S can be, the bound is S is greater than or equal to 0, but S should be at least 1 for the whole thing to work, is obvious. If S is equal to 0 means won't work. So to be very precise, S should be greater than or equal to max of 1 comma n minus prime of A. And then we can also think about a Kalman decomposition type procedure, which can decompose the state space into controllable, sparse controllable, controllable and uncontrollable cases. So within the controllable space, we can again decompose it as sparse controllable and sparse uncontrollable space and uncontrollable space. I don't discuss the details, but we can check a paper if you like. Another interesting result here is the number of sparse control inputs. So once we have a time-varying system and we know that it is controllable, then the next question to ask is how many number of inputs are required to guarantee controllability. And this is our research for that. So might look a bit ugly, but I tell you the main takeaways from this. So the number of control inputs identified by K star is bounded by n, which is a dimension of the state, which is also also has similar bound in the classical control theory. But if you look at the exact bound, it decreases with S. So S is a sparsity level. So if you the most sparser your system is, you need more number of inputs, and if you allow for larger S, you need fewer inputs, which is kind of intuitive. And if you look at this term, the lower bound also has an S sitting here, so the lower bound also decreases with S. So this decreases as 1 over S, and this also decreases as 1 over S. So the more the S is, the fewer the number of inputs that we need. It is kind of trivial. And what is interesting is, however, what the sparsity level is, at most we need n number of inputs to control the system. Well, this is a very, very important result when it comes to the design of sparse controls. We have other extensions of sparse controllability. So for example, so this is what we discussed. We'll fix about the rank of A minus lambda A times big sub S should be equal. Its sparse controllability is when system should be controllable and S should be larger than or equal to n minus rank of A. Another extension is sparse controllability with non-negative sparse inputs. So if you only allow sparse inputs which are also non-negative, how does the condition change? The condition changes net effects in an expected fashion. So we have to replace controllability with non-negative controllability, and the sparsity condition remains same. So again, this is for time varying sparse support case. We have similar results called output sparse controllability. So for output sparse controllability implies, so you have replaced controllability with output controllability, and the bounds on S is slightly different. It's again, so I don't put it here, but we have some bounds on sparsity level which can ensure output sparse controllability. We can also look at sparse stabilizability. So we have a system. When is the system stable? Can you make the system stable only using sparse inputs? The answer is yes, and Sparse stabilizability is interestingly equal to stabilizability, and there is no bound on S. So if the system is stabilizable, it is also sparse stabilizable, even with S is equal to 1. So it echoes S is equal to 1 inputs to make the system stable. But all these three results assume that we're looking at time waiting support case. Alright, so this kind of summarizes the controllability results we take it to sparse controlled inputs. Any questions so far? Okay, now I'll quickly move to the design of controlled inputs. I don't have many slides here, but I'll quickly tell you what is the high-level idea behind designing sparse controlled inputs. So the question here is, I'm given an initial state and a final state. How do I choose my sparse inputs? So if we recall, if the system is sparse controllable, we need at most N sparse inputs to control its system. So one way to solve this problem is to write out a classical durability equation. So I'd say x final minus k times x initial is equal to the durability matrix times all the inputs that we've analyzed so far. So how is different from the classical control design formula? Here we impose a condition that each of the UKs should be sparse. So U1 should be sparse, U2 should be sparse, and on to U. Each of the piece of the control, the big long control vector should be sparse. That is the only difference. So you can see this as a linear system of equations. So I call this as x tilde, and this is p, and this is v2, which is a big long vector of all the inputs that I have to apply, and I get a system of linear equations. If there are no sparsity constraint, I can just use a least square solution and find out what is my huge corresponding energy input. But we have an extra constraint that U should be sparse in this case. So there are two options to approach this problem. The first one is a compressed sensing based approach to solve this problem, and the second one is sparse actuator scheduling based approach. So in the compressed sensing problem, if you look at this, we are trying to solve a linear system of equations with sparsity constraint of U. So that is exactly what compressed sensing problems also solve. So in compressed sensing, we have a linear system of equations, and we have to solve for the unknown with sparsity constraint. So one naive approach is to apply the standard compressed sensing algorithms to estimate what U is. But the catch there is, if you do apply the standard compressed sensing algorithm, you won't be able to impose the sparsity condition on each of the UKs. Because compressed sensing algorithms look at the sparsity of the entire vector, not individual pieces. So another option is to exploit this particular structure, where you want to ensure that every piece of your input is sparse. So this kind of a sparsity is called piecewise sparsity. So for example, think about this as your big long vector E, and these are zeros, and spikes that you see are non-zeros. So if you look at this big vector with about 250 entries, this is a big long vector with mostly zeros and few non-zeros. And this is a general sparse vector because a non-zero entries can be anywhere. So the only condition is, out of all the 250 entries, very few entries are non-zero. This is the notion of sparse signal, which is what the compressed sensing algorithms are looking at. What is piecewise sparsity? Piecewise sparsity, we again look at a big long vector, but we divide this vector into small pieces. So the small arrows, lines here, represent the different pieces. So piecewise sparsity imposes an extra condition that every piece should be sparse. So this is exactly what we need for controlled inputs, because we can think about one piece as one input. So this is U1, this is U2, this is U3, and so on and so forth. And we want to impose a condition that each of these pieces are sparse. So this kind of sparsity is called piecewise sparsity in the presence in literature. And there are specialized algorithms which can be used to solve this. So there are algorithms called piecewise orthogonal matching pursuit, and so on, so to solve these kind of problems. So this is for the time varying case. Now let's look at the time invariant case. In the time invariant case, where we have to solve a system of equations, but there the difference is that each of these UKs should have the same support. So if the first entry of U1 is non-zero, the first entry of U2 should be non-zero, and so on and so forth. So you can look at that big long vector, it looks like this. So the first entry of U1 is non-zero, the first entry of U2 is non-zero, first entry of U3 is non-zero. So the second entry of U1 is 0, the second entry of U2 is 0, second entry of U3 is also 0. So the sparsity pattern repeats. So one clever trick that we can use here is, we can pick all the first entries of all decades. So I pick the first entry of U1, first entry of U2, first entry of UP, and call it as one block. I pick the second entry of U1, second entry few t, and second entry few 2, and second entry few 3, and followed by second block, and so on and so forth. So once you do this kind of a rearrangement, we get different blocks, and these blocks can be either all non-zeros or odd zeros. So for example, here first block is non-zero because the first entry is a non-zeros for all inputs. The second block is 0 because second entry was 0 for all inputs. So once we have time invariant support, we can rearrange this U vector into a block sparse vector. So this kind of a sparsity pattern is called a block sparsity pattern. Block sparsity means you have a big long vector. The vector can be divided into more different blocks, but every block can be either full non-zeros or full zeros. The total number of non-zero blocks is going to be very small compared with the total number of blocks. So we have fewer non-zero blocks compared with the total number of blocks. So this kind of sparsity pattern is called block sparsity. So to recapitulate, in the time varying case, we have something called piecewise sparsity. They didn't rearrange, we just divided the big long vector into small pieces. In case of time varying support, then support remains the same. We have to rearrange the columns to get something called a block sparse pattern. And now once we've identified the sparsity pattern in U, what we get do is we can apply the compressive algorithms. So this is a illustration of the three different sparsity patterns. The first one is a ripple sparsity pattern where the non-zero variables can be anywhere. Second one is the block sparsity, you just what we get for the time invariant case when the support is constant. So we get blocks of non-zeros. The last one is piecewise sparsity, which is for the time varying case when the support changes over time, and therefore we get something called piecewise sparsity. And there are compressive algorithms which can solve for these different sparsity patterns. So if it is time varying case, we have used piecewise sparsity algorithms. There were limited algorithms here. There's something called piecewise OND, piecewise inverse VLSS algorithm, etc. And in case of time varying, we get block sparsity, and there are a lot of algorithms like block OND, block SDL, null of SDL, loop lasso, and so on and so forth. Okay, so this is one approach to design sparse control inputs. But the limitation here is we have to solve a system of linear equations every time. So if we make a small change to the initial or the final state, we have to start from scratch. So we can solve the compressive algorithms for any given initial state and given additional final state. But if we change one of them, we have to again do all the operations from scratch. So another alternative which can mitigate this problem is called sparse actuator scheduling. Recall that we said if we have a time varying or time invariant case and the system is controllable, there exists a schedule which goes for all initial and final state. So another way to design sparse control input is to try to identify this schedule. So for the time varying case, we can try to identify the set S1, S2 on the SK such that the corresponding Galvan partition is satisfied. So the corresponding controllability matrix should have full rank. This is a combinatorial problem, and people have proposed very algorithms to solve this problem. And for the time invariant case, the only difference is we have to put S1 equal to S2 equal to SK. So we have to look for a set S such that the corresponding controllability latent is full. And once we amplify the schedule, whether it is X1, S2 or SK here or the set S here, and then we don't have sparsity constraints anymore. And now we can use a least square way solution to find the sparse vector. So this is different from the compressing approach, because in the compressing based approach, we have to solve our sparse inputs for any given initial and final state. But here, we can first solve for the schedule, and once we have the schedule, then for any initial or final state, we have to just apply least square solution, because we already know what the schedule is. So these are two different approaches that we use in literature. So to summarize, so we looked at sparsity constraint, which means we are restricting our aggregate inputs compared to the classical case. There are two things that we looked at. The first one is the time varying case, and the second one is a time invariant case. So this should be time invariant, this should be time varying. So in the time invariant case, we use block sparse algorithms, and the corresponding controllability condition is that the system A times Bs should be controllable. And for the time varying case, we look at piecewise sparse algorithms, and the existence condition or the controllability test is that the system should be controllable and sparsity level should exceed the nullity of A. So this is one slide summary of all we discussed today. We also have a bit of work in structured analytical systems, but I'll skip it for the time being. Maybe some quick comments for open problems. So there are different types of sparsity constraints. So sparsity over time, which is one the next speaker going to talk about. Then I got the more sparse actually to use. There will be sparsity in feedback control, etc. Then the design algorithms are very limited at the moment. So we have a lot of opportunities in that sense. For example, the piecewise sparsity algorithms are not very prevalent. There are very few algorithms which can do it, and that too are greedy heuristic-based algorithms. People have looked at deep learning-based approaches or more sophisticated algorithms in that way. In sparsity plus structural vulnerability, which I didn't talk about today, is almost untouched. So that area is completely open, and the analysis that we do for the classical analytical systems perhaps will also be explored for the structural analytical vulnerability case as well. So thank you for your time. If you're interested in this topic, I would refer you to a monograph which I recently published in Partitions and Trends in Systems and Control, so which is a very simplified version of what I talked about. If you really want to know about it, you look at the papers, but this has a more simplified, I would say, layman's way of explaining things, and the proofs are also much simplified than the original paper. So if you're interested, I would really recommend the orange reference here, but this is the list of other papers that we have published recently. Thank you. Any questions?
Okay. Can you tell a little bit in Soji why the safety condition there, the s greater than or equal to, is get necessary?
Necessary is simple, that's what I... Or no, efficiency. That involves a bit of a proof. I don't want to explain that here. Okay. So basically, you can construct a sequence of schedule. You can show that if there exists a sequence of schedule which can actually satisfy this condition. Yeah. If you just be discuss it offline, yeah, it's hard to discuss it here.
So you consider the piecewise sparsity.
Correct.
And the partition is uniform, right?
Correct.
So can you consider non-uniform partition?
The uniform partition is because of the structure that we have in the problem. So if you look at the big block vector that gets solved for other inputs, the size of the input is the size of one block. So this is block 1, block 2, and that block added. So the structure as we use the same, the length of the contour ripples remain the same over time. And that's why we have equal sized piecewise task block. But that is not very critical from the algorithm's perspective. For an algorithm, you just need to know the block boundaries, but it could be different blocks can be of different size. So this may be that.
Oh.
But my analysis assumes that all the UIs have the same size.
So in the slide where you mentioned the open problems, so there are 1.1. What? Yeah. Or you mentioned feedback control. Yes. So does it mean that you just want to make your controller, which is closed loop, sparse, or do you want to specify somehow the measurements that you are getting?
It could be either way. So one thing I've seen people doing is they make sure that the feedback that goes back is sparse. So the K matrix I normally multiply. So basically it's a close feedback as the encoder thing becomes K times the states, right? At K matrix, make sure that K matrix has row sparsity. So K will have a lot of 0 rows so that the control ripple becomes sparse. So that is one notion of sparsity that. Another thing is they take you can look at case that K matrix itself is sparse. They need not the row sparse, but the sparsity could be anywhere. The idea is you have to make fewer commutations. You represent K as commutation between different nodes. You have to win the commutation, so okay. Feedback matrix needs us, the K matrix.
I'm interested in whether the two different hierarchies kind of work together. If I had a huge problem and I apply some sort of time invariant thing first to find here's the only place I need to put my sensors of actuators, and I then apply time variant one to say, of the smaller set of control inputs that I have selected to be worth putting in the system in the first place, then can I do the time invariant one to only switch certain ones on at certain taps?
Do you want to use time invariant for some time and then you want to switch to time?
No,
Time vary for some time and then you want to switch to time invariant.
I'm asking, can you apply both techniques to take a really large number of potential inputs, down to a smaller set, and then down to an even smaller set?
I've not tried that, but I think that's a very interesting idea. But probably you should be looking at some sort of stabilizability problem there. It cannot be a controllability problem, I assume. Maybe a step. So basically, you can try to pick few actuators, the time varying actuators initially, and stabilize your system or drive your system to a desired state. That probably apply. Only use a few actuators from there to stabilize your system and there. Oh yeah, that could be a good idea. Good question that I haven't tried yet.
And for the actuator schedule, so you said you first find the schedule and then you do the least squares. So I guess there are several schedules that would work, right? So could you find an optimal schedule somehow, or like the best one that uses the least inputs?
So here, you're right. A lot of schedulers can work. So the condition that we impose is we quantify the scheduler such that each of the SIs have the minimum sparsity level. So we import them.
needs the S not smaller than S.
Yes. So basically, you have this S greater than or equal to n minus that of A. That is the basic condition. So we assume that that is the lambda sparsity that allow, and then we can find the scheduler. But if we have more roots, so this is more of a system constraint. So if we have more root, then perhaps you can take it as a trip. But what this is trying to solve is to find schedulers such that each of the SIs has a minimum number of entries. And there could be multiple solutions there as well. So if let's say that S50, S is equal to, let's say, n minus lambda of A, which is the bare minimum that we need. So if you go down, then you get up. The system is non-controllable. But even if you pick that particular sparsity level, there could be multiple solutions. So the one way we approach the problem is we find the solution which leads to minimum energy. And the energy be defined in terms of the eigenvalue of the gravity matrix. So that's, or it could be traced. There are multiple notions of minimum energy there when it comes to scheduling problems. But you are right, there could be multiple solutions even after inversing sparsity, and then we might need another notions of optimality. Could be eigenvalue. Something.
Cool, thanks.
My name is Masafino Bakara, and today I'm talk about sparse control for continuous time systems. Okay, so this is the table of contents, and first of all, I prepared a review of sparse optimization. This is a very basic, the basic part of sparse optimization. All of you knows this about this, so I'll omit this due to the time limitation. But I focus on the one fact that in compressed sensing or sparse signal processing, sparse signal construction, we consider linear equation here, and the phi is a measurement one matrix, and we try to reconstruct sparse x from the measurement y, and the important point is that the size of measurement is less than the original size of x. For example, we have the original sparse vector here, and by the measurement, we obtain the small size of data. And from this small size of data, we try to reconstruct the original sparse signal. And the idea of sparse signal reconstruction is to consider this tail zero optimization. However, this problem is very difficult to solve because this is a LP hard problem. So in signal processing or machine learning, they consider L1 problem here instead of L0E, this minimization. And this problem is very easy to solve. And actually, if I have this measurement and if I know the matrix phi and solving this L1 optimization, I could exactly reconstruct the original sparse signal. So the L1 normal optimization is a very powerful and effective tool to solve the original A0 optimization. This is the main basic idea in compressed sensing. And I will use this idea to optimal control of continuous stars and systems. Okay, so I loved this. Okay, so I will explain the maximum method control. Okay, so we consider sparse control something like this, and this control signal, this is a continuous time control signal, has some time duration here over which the control, the value of control is exactly 0. This is called the sparse control. And in control systems, actuators such as electric motors need energy to generate power, and by this sparse control, we can stop the actuator or energy supply to the actuator during this time duration. So this is a very nice property to save energy to control something, and this is called hands-off control. Okay, and this is also known as costing, and by using this kind of control, we can also reduce CO or CO2 emissions and the noise and vibration between these during this time duration. So this sparse control is also very nice for environment. Okay, so this kind of control is very important in reset control systems. Okay, so and actually we can find many examples in the real world, examples of hands-off control. For example, start and stop system in vehicles. This is exactly the sparse control, because the engine is stopped when the vehicle is stopped. So and also hybrid cars are also considered as hands-off control system, because the gasoline engine should be stopped when the electric motor works. So and also the electric locomotives. This is also this uses sparse control and hands-off control between two stations. Okay, so they operate the locomotive as sparse control. So we can find many examples of hands-off control around us. And theoretically, hands-off control or coasting is also utilized the event trigger control. And the important point is that the purpose of the maximum hands-off control is maximization of the time duration for coasting or hands-off control, which is not considered in event trigger control. So we formulate this problem as an option control problem. Okay, so we consider the mathematical formulation of the maximum hands-off control problem. Yes. And for that, we need the definition of L0 norm for continuous time signals. Okay, and the definition is very similar to the L0 norm for vectors. So we consider the support set of a function like this. Okay, and the L0 norm of a function for continuous time signal is defined by the length of the support set. Okay, and the mu is the length or the Rubel measure of function of the support set. Okay, and this is the L0, and this L0 is the total length of time durations on which the signal takes on the values. So we can say that if the signal has a very small L0, then we can say that control signal is sparse. Okay? This is the definition of L0. Okay, and with this definition, we can formulate the maximum hands-off control as an optimal control program. Okay, so we consider linear time invariant system, continuous time invariant system like this, And we consider single input case for simplicity. And we are given the initial state anxiety here, and this is the key to initialize. And for this system, we find a control over the horizon 0 and t that minimizes the L0 of control. Okay? And also we find the control that satisfies the final state is 0. And also we restrict the maximum value of control to be less than 1. This is the L0 control, and the L0 norm can be also rewritten as the interval for this. Okay, but this is the L0 optimal control, but this is also very difficult to solve because the cost function is non-convex and discontinuous. So we need to approximate this problem to some easier problem. But borrowing the idea of convex sensing, we just change the cost function to the L1. And this L1 norm is a convex function of U, and this problem is actually very easy to solve. And this is very well known optimal control problem called and very classical or minimum fluid control. So we can easily solve this problem for linear systems. And but the problem is that if the solution of this L1 optimal control identical to the L0 original L0 optimal control, this is the problem. But I will show some equivalence between L0 and L1 optimal control progress in the next section. Okay, so we are considering the L0 and L1 optimal control progress, and we use the parameter P is 0, then P is 0, then we consider L0 optimal control, and P is 1, P is 1, then this is the L1 optimal control. But we obtained a nice property of the equivalence shown in this theorem, and we assume that there exists at least one L1 optimal control, and we also assume that the pair AD is controllable, and the matrix A is non-singular. Then there exists at least one L0 optimal control, and the set of L0 optimal controls is equivalent or is identical to the set of L1 optimal controls. So if you want to obtain the maximum hands-on control for linear system, you just look at the controllability of the system and the matrix A. If the matrix A is non-singular, then you can just solve the L1 optimal control, and you can say that this is also the L0 optimal control. Okay, so this is very nice theorem. If the A is non-singular. Okay. So this is the theorem, but if A is singular, the matrix A is singular, then there exists an initial state x0 such that the L1 optimal control is not L0. So if A is singular, then you cannot use L1 approximation. Okay. And this theorem also shows the existence of L0 optimal control under the assumption the existence of L1 control when A is non-singular. And later we will discuss the existence of L0 optimal control or original maximum hands-on control even A is single. This is the special case, but we can find many examples of systems which has single A. For example, we have integrator or double integrator, which has feature A which is similar. So we need to consider the case when A is single. Okay, so to consider that, we first analyze the original L0 optimal control, and by using the maximum grace group or non-smooth optimal control programs, we obtain some necessary conditions, and we omit the details of this, but the important point is that for the necessary condition for this optimal control, we can say that in any cases which we in A is singular or non-singular, the L0 optimal control always takes only 3 values, plus minus 1 or 0. This is very important property of the maximum kinds of control. And the L0 optimal control, or the maximum hands of control, is something like this function. Okay, and this has these are values 1 and minus 1 and 0, just 3 values. And we call such control band optimal control, because this is the band part and this is the off part. Okay, so this is a very important property of maximum hands of control, or L0 optimal control. Okay, so then we consider the existence of the L0 optimal control even if A is singular. So for that, we first define the feasible sets of the optimal control program, and the feasible set is denoted by U. T xi t is laboratory lex, and xi is the initial states. Okay, here initial states here. And this feasible set of control is described by this. And by using this, we can say that this feasible set is non-empty if the horizon x t here, horizon x t is strictly greater than t star, which is the minimum time from xi to the origin. Okay, so if the price range is strictly greater than the minimum time, then the feasible set is non-empty. Okay. So now we consider the existence of L0 control, but before that we consider empty optimal control with P greater than 0 and less than, strictly less than 1. This is a non-convex, also non-convex physics problem, but this has a very nice property, LB optimization. And we have one simple theorem that if suppose that LP optimal control here is P less than 1 exists, then the set of L0 optimal solution is equivalent to the set of Villepio solutions. So namely, if you can solve this non-convex optimization problem, then the solution is equivalent to, but identical to the original L0 optimal control problem. If you can solve this, then you can obtain L0 optimal control even if A is singular. Okay, but this is non-convex problem, and I will explain how to solve this later. But now we have this theorem, and also we have another theory saying that suppose that the horizontal density is and xi are chosen such that the field set is non-empty. Okay, field set is non-empty. Then there is this LP optimal control with P greater than 0. Okay, this is another simple theorem, and using this cell, and this cell, combining these two theorems, we have this theorem. Okay? If the feasible set is non-empty, then there exists an L0 solution. Where is the L0 optimal control? Okay, so this is a. You may feel this is obvious, but to solve this, to prove this, we need many lines in mathematical properties. However, this is very very nice property. You can just take the horizontal t, which is already greater than the minimum type. There you can say that there exists an L0 solution. There only you need to do is you to focus on how to solve the for example the LP optimal fundamental with P less than 1. Okay, so we extend this idea to more general non-convex functions. Okay, so the optimal control probability in general is securely written as this. Okay, this is the feasible set, and we assume that this feasible set is non-empty, taking t greater than the minimum time, and minimizing this function over here. And this side, this is a kernel function, and if you use the LP, the absolute value to the power of p, then this is the LP norm. And also we can consider and this the important point is that this function promotes the sparsity of the function. And also we can consider minimax concurrent function described by this complicated equation, but I'll show the shape of this function. And the shape of this function is something like LPO. Okay, and this is a very nice. This has very nice properties. And also we can consider L line minus it, which is defined by guess here absolute value minus the square. Okay, and this also promotes sparsity, and we plot these graphs of the functions. The blue line, this is A1, the kernel A1, and the orange line, this is the LP node with P equal to 0.5. Okay, the shape of this, and the minimax concave penalty is green line, and the M1 minus L, this is something like this, and these are they are non-convex function, but they can promote they can lead to sparse control or maximum control even async. Okay, so this is the nice result of that, and suppose that the feasible set is non-empty, and suppose also that this function has these properties. Okay, you can check these properties easily, and the LP node minimax concave penalty and A1 minus then two functions satisfy these assumptions. Okay, then there exists an optimal control to this, so the existence is all existence holds, and also the set of all solutions to this property is identical to the set of the original L0 optimal controls, even async. So if in summary, if you take t greater than minimum time, then feasible set is non-empty, and then the L0 optimal control exists, then you can just solve this optimal control problem with phi satisfy these assumptions. Okay. And so then how to solve this optimal control problem? So the problem is solved by using time discretization. time discretization. Then, by using time discretization, we obtain finite dimensional vector optimization. Okay, but the loss function is still non-convex. However, the non-convex function has a nice property that the optimization discretized optimization problem can be solved by difference of complex functions. Difference of DC program, which is difference of complex functions. Okay, and also the function phi is minimus on the general field. Then this function have very nice property that we can solve that by using the forward-backward algorithm for convex optimization. So this can be solved much faster than this. Okay, so you can choose and the function phi as mass for given person and the optimization person. My PhD was about formulating the proof of Kepler's conjecture that states that the optimal way to pack oranges is the intuitive way. That was a conjecture until 2040. So it was one of the oldest conjectures, 400 years old conjecture that Kepler made in his 60s son. And so to solve this problem, you need a huge computational proof, and you have some nonlinear inequalities relating the angles between the different centers of the oranges. And so there is some kind of sparsity when you look at it, because you don't have only polynomials, you also have square roots of polynomials and also rational, heat divisions of such quantities. And you can transform this into a polynomial optimization problem by lifting the square roots. We will say that u is the square root of w is u squared omega v and so on. And these new variables that you introduce are not connected to all the other variables of your. So that's how I got crazy these passes.
What makes it why is to excited about this topic? What is that fun to you like?
Also because so I did my PhD from 2010 to 2013, and very often people claim that these hierarchies of NMIs they do not scale, and but they are doing a lot of efforts to try to make them more scalable. And many different notions on sparsity have been introduced, so I only mentioned two in my talk. And like recently, there were like two contributions by young people in their PhD to tackle sparse dynamical systems, analysis and control. And so this basically, these young people, they have a fresh view, and they basically invented new types of sparsity context of polynomial optimization. So this is still a very lively area. I hope there will be new stuff in that.
Thank you.
Okay.
I'll read this up.
I hear it. I got to my PhD 20 years ago, and my subject was signal processing problems, and but not the standard signal processing. But I used the H-infinity control theory to design some linear figures, and at that time I attended some signal process conferences in 2010 or something, and at that time the sparsity or compressed sensing was very hot topic in signal processing, and but in control community, not so many people know about compressed sensing, but I was very interested in that topic, and I always considered how to apply this nice usage of between the control systems, and so I have one application of that Marshman hands-off control, and at that time also they in signal processing community they also did many applications of sparse optimization. So they found some applications to some make photograph of the black hole. There's a big project. This is a big project, and some team
use the compressed sensing technique to reconstruct the black hole shape using the sparsity and so on. So I think this sparse auto, we should find some real applications to which is very good for real world, because sparsity is related to some energy saving or some very good for environment. So application of this topic is to consider the applications.
Okay, speaking about applications, so we heard about a lot of theory today, but what is your take on practical applications of these things? So where can we make an impact, or is there an industry that we can collaborate with and make an impact using sparsity? Where can we save? I mean, interpret people say sparsity as a way of saving, right? So where can we save? Or where can we make a social impact using sparsity? What is your take on that? Or are we not yet ready to go to that stage yet?
So to start.
So, because I don't work very much with industry, I think, like, I'll talk about neuroscience set because I want that side. So like neuroscientists actually, they do actually like control theory, at least a substantial portion of them do, but they're very much still in the like classical linear 101. Like, here is my controllability matrix, which we saw a bunch of times today. Like, here is the gradient. I think, like, as we have more mature methods of sparse control, I think this will maturate directly onto the things that they're doing. So it like also preceded helping that. So I guess that's what I'm saying, that we make these nice theories that are like one more step away from the classical controllability notions, and then something that they can use for analysis that I think can be best. Yeah.
So I work a bit with industrial people. In France, there is this French energy transmission operator called RT. And so they want to solve the so-called optimal powerful problem. So basically the electrical network is a huge graph where you have some nodes, some generators. And all the nodes are of course not connected to each other. So basically to solve these problems with 6,000 variables, powers and voltages, that is a non-linear and convex problem. You need to exploit sparsity. So we have been collaborating with them for a couple of, for 5-6 years.
So it actually was.
There is a direct application of our stuff. So I will be very honest. So the problem is that semi-definite programming is not used in the industry yet. But that might change with this energy transmission operators. And also because of another new application that makes a lot of noise, and it's called quantum information. And so there is also sparsity when you look at these quantum information protocols. That's a bit far from this school, but just to mention it. So basically some quantum information problems related to quantum cryptography can be written as polynomial accumulation problems. And also that there is some sparsity because Alice and Bob do things that somehow could use. So yeah, so there are concrete industrial forthcoming applications that will maybe also drive the development of convex optimization solvers that we use in our academic area, but that industrial people do not use yet. Beyond this.
Do you have some industry implementations, Dominic?
This is once I collaborated with some automotive company and work on the engine. However, there's no piston wheel for the forward, but there's just a simulator. Okay, and there are many inputs, and also there are many concerns. And for that, I couldn't do some, for example, optimal control or some model probability control, and they just use PI using simulator, and every day they tune the PI parameters, and some mature people can tuning the PLD out of the video nicely, but when I try to translate that into optical control, then there are very big gap between theory and real system, and this is very challenging and when I tried that to write that program, then I realized that the real systems are very highly nonlinear, very complex, and there are too many inferences and so on. So this is very nice to know that to consider theoretical progress. That is very nice to know there's real stuff.
Thank you. Let's discuss some topic. One of the themes of this morning has been that we've seen sparsity mean lots of different things, right? Sparsity in time, sparsity in the number of active controls or whatever. So the question of the discussion point is, these things seem to be connected to each other somehow. You talk a little bit about where you see these connections. If I was pitching it as a sort of neuroscience question, it would be the brain is clearly both sparse in the number of signals that are active, but also it's sparse in time, right? Like it's a spiking system that seems to have both of these properties. Do you have any thoughts about connections between these different kinds of sparsities or something like that? Is it the same phenomena, just expressed in different ways, or are they fundamentally different, and do they have different properties? Are they useful for different kinds of things? Can we exploit them all at once? Are they incompatible? What's the thing?
Maybe mathematically it's the problem of the L0 optimization, mathematical, and to obtain sparsity in time, or to obtain sparsity the number of actuators, the problem is to find which are non-zero, and this is a combinatorial formula, so this is very hard to solve. So I think the mathematical problem, mathematical difficulties are the same. But concerning application, they look very different. The underlying mathematical model is very similar.
I don't agree with that statement, but my take is sparsity in actuator scheduling, actuator use versus time are two different paradigms. There are some tools which we can use in Goblin, like Albino, example, Elseron. But I think fundamentally these are different problems, and there could be a lot of intersection as well. So, for example, we can try to look at sparsity in actuator use and sparsity in time, like both together. Like how do you sparsely control things? Like you have to do both at a time. And so there is sparsity in communication that can also be brought in at some point. And I think these are more interrelated, but the underlying mathematical frame or tools would be same, but there are different fundamental problems, and there could be a lot of options to do mix and match and get away in the disciplinary things here.
I also agree, so I think it was more the last things that you said that for me are the most relevant. So in the case of polynomial optimization, we have basically at least 3 or 4 kinds of sparsity today, and they are very different. We can basically illustrate things that are sparse with respect to this thing, but not with respect to these 3 others, and we can also combine. So, as you say.
Right, the notional sparsity is kind of dispersed. He planned to be at an isolated places, making they should the platform should come together and become things.
I think the general theme, at least when I think about like neuroscience, is that it's sparse along like communication, actuation, sensing, and so on, tying in tempo encoding, but like it does honestly better than our robots. But like I think the general theme that we saw today is you can have a lot of sparsity and not lose too much, if at all. And then if you were trying to put a bunch of them together, I think then it starts coming down to a question of like relative energy. Like, do I save more energy by completely getting rid of this actuator, or do I save more energy by like physically having it, which is costly, and then using it once in a while? So it becomes kind of like a weighted co-optimization of sorts.
yeah, I think it relates also to this question of how conservative are the bonds when you explore sparsity. And so maybe I wanted to emphasize that there was something that I think no one among us mentioned, that is the exploitation of symmetries. So the exploitation of symmetries is much better, right? Once you have detected them. So of course detecting them is very hard. But once you have detected them, it's very good, because then basically a lot of like dense matrices will block diagonalized. And you will have meta conditioning, and also you don't have conservativity. So maybe also a relevant question is how to combine symmetry exploitation, sparsity exploitation. There is, I think, a non-trivial task and has not been looked at so much. I mean, with my classes of polynomial optimizer, I see what kind of problems could be, but I don't know what you think about that.
So it feels to me that a lot of the combinations of sparsity come from, in the case of the braid. The braid is such a powerful machine. You can do so many things. It has lots of space that Pierre Volbert returns in Thailand in number of activities. I suppose it's true that for applications, we kind of do that already by just setting up my problem in such a way that we're not going to add a whole bunch of redundant actuators to a system that we know we only need 3 actuators for, and vice versa.
You need to add one in because sparsity, as you mentioned, is a big thing. It's a big possibility. 20 years ke commit to compression check or a familiar things like that. But when I look at the control theory sparsity, people normally just restrict themselves to L1 log and won't go beyond that. So, but if you look at the signal crossing, the sparsitive crossing area, there's many more algorithms, there are many more ways you can tackle sparsity. So maybe that is one object. Okay, other questions?
Yeah, so I have one more question regarding the sparsity in terms of state measurements. So are there any results where not instead of measuring the whole state, where for the inner controller k multiplied by x, or not instead of sensing or measuring the whole state x, or just going to measure some elements from them. So are there any works on this?
The sparse control, look at the distance I showed you today, and we look at the sparse observability document. Okay, so they're duets basically. So the question is, can you select fewer sensors at a time, and still everyone start your reach will say that's the same question. So this is like observability and observability, these are duets, and you can exactly the same. So if you want to make sure sparse observability, your system should be observable, and the number of sensors that you pick should be around equal.
Okay, okay, you pick it the
Same question.
Okay, time varying, yeah.
The questions.
Yeah, I'm
We
wondering.
call them desperate. You have your question.
Okay, yeah. Yeah, I was wondering if there are any connections between like multi-rate control and sparse control. Because with multi-rate control, you send like some actuator signals at a certain frequency and others at a different frequency. So there's a sparsity pattern in the control, but it repeats kind of. Like if there are any, I wonder if you looked into that or know any connections.
So that would be sparse in the frequency domain, as opposed to sparse in the time.
You know, like sometimes like you have a control input that you calculate at every time step, but then there are some that are calculated at a different frequency, or like, sorry, it's every second time step or every fifth. So then you have like a repeat.
Fast sparse on is like control.
Yeah.
If you define it as a function of the delta, very good. There is next part. Welcome. In 5 comments. Let me reward share the last thought that we want them to take away from this session. Or
Well, many thanks for
yeah, if you don't have anything else, then let's conclude this workshop. Thank you so much for editing, and hope you learned something from this and this inspired you in some way or another. And you can interest in this topic, the collaborate with partners. All of us have put your applications over. Thank you so much.